Okay, so today I thought we'll take a look at one more example on PCA, Principal Components Analysis, and then on Wednesday we can start. We'll go back and do the chapter on clustering. So this example comes from this textbook, a handbook of statistical analyses using R. This is a very broad textbook, but I would say it's worth checking out, especially if you're curious about how to do a certain kind of analysis. Each chapter is very terse, so if you're trying to learn a concept for the first time, probably not the best textbook to use, but it's got some good examples. And oh, you know what? Okay, I'm gonna have to. This is the wrong chapter that I've linked to. Okay, ignore this link. I'm gonna have to find the right link. Okay, let me just kind of describe the data that we're going to take a look at, and we're going to look at Olympic heptathlon data. Okay, so this is from the 1988 Olympics held in Seoul, Korea, and it was we're looking at women's heptathlon. Okay, so heptathlon, there's like there's seven track and field events in which people compete. There's like hurdles, high jump, shot put, 200-meter run, long jump, javelin, 800-meter run. Okay, so there's like 7 different things that they compete on, and then we have to boil. So we basically have 7 dimensions, but then we have to rank them, and we want to rank them so that it's weighted properly, right? And but each of these things, you've got 7 different things that they're competing on, and then there's this question of like, okay, one of them you're like throwing a javelin, and then others you're like running, and we want to know how do we score these, right? How do we compare the scores that people get? So I'm going to load up. You might have to install this package, HSAUR3, which is the kind of the data package that accompanies this textbook, and we'll load that up, and we can take a look at heptathlon. All right, and then so actually let's do view heptathlon. Okay, and so here we see Jackie Joyner-Kersee. She had the highest score, 7,291, and these were her individual things. So you get hurdles and high jump, shot put, the run, long jump, and so somehow we want to turn these 7 different things into a single score. Okay, and so this score, this is determined by kind of the rules of the International Olympics Committee and all of that. But what we can do is we can kind of just take a look at some of these things here, okay? And so one thing we can do is we can just kind of create a plot, and we'll plot everything in heptathlon without score. Oops. What did I do? Oh. Okay, sorry. First I've got to I'm going to take the column names and identify which column is equal to score, right? And then it says score, sorry. Score is the 8th column, so I can just say plot everything without the 8th column. Okay, and so this kind of creates pairwise plots here. And to make our analysis a little bit better, we're going to flip the kind of the order on some of these variables, right? So you know, if we look at things like long jump and javelin and you know, shot put, higher scores are better, right? Like the farther you throw the javelin, that means you are a better athlete. You're better, you're better at that event, right? Whereas when you run hurdles or you do the 200-meter run, lower scores are better. So we want you know, faster times are better. So we're gonna just we're gonna flip some of these around, all right? And maybe we'll just kind of zoom in on some of these plots because this is just too many at the moment. Okay, so for we're gonna just redo the hurdles, and we're gonna say heptathlon $hurdles. What we're gonna do is we're gonna take the max hurdles score or the slowest time, and then we're gonna subtract off everyone's time. Okay, and so it'll be kind of like so this will now be the amount of time they finished before the slowest competitor, right? So we'll just reorder heptathlon hurdles, run 200 and run 800. And so this here, I'll fix this and I'll upload it later. So we will reverse the order of these events so that larger values mean better performance. Okay, and that will just kind of help our analysis. Okay, and then so we'll plot this, and then this I ran it again. Okay, so here we go, and you know what, let me just when we if I just do like the first 3 columns and we do a plot here, okay, we see that there's a person, there's kind of like one value that is like much lower in performance than everyone else, okay, and so I think to aid our analysis, we're going to remove this competitor just because you know, looking at everyone else for hurdles and high jump, this person's performance is much lower, and so we can do a little exploration, and we'll say, you know, we notice there is a very poor performing outlier. Okay, it's a little. Have you guys seen? I forget which movie it was. Some movie about basically. Okay, so here we can kind of. I've already done the thing where. Let me just load up. Okay. Okay, so that exists, and then if I. So this is kind of our correlation with the outlier included, and over here we're going to just remove the person that has that's the outlier. If we kind of just look at the if we look at this, we see kind of, you know, even just looking at the scores, we see Lana from PNG. I think Papua New Guinea has a very low score here. Okay, so we're going to remove this person. Okay, and so we do that right here. Okay, and then this kind of improves all of our numbers. And we can, you know, we can kind of do a new plot.
Why are we removing a plate when it's like valid? Like it's not like an error.
It's not an error, but it will throw off our analysis a little bit. Okay. So for example, if like I went to the Olympics and I competed, right? I would have absolute terrible scores on everything. And then if they were to try to come up in the scoring system, right? Like you're trying to design a scoring system that distinguishes kind of like athletes from each other in the top echelon of performance. And so if your scoring system tries to also accommodate your regular, like, not people who are not Olympic athletes, right? And if you're scoring, like, your scoring system will not be very good, okay? Because you're trying to come up with a way to distinguish top performers, right? So, for example, like, if you gave the MCAT exam, right, to like junior high schools students, okay, is this going to reveal anything to us about the relative performance of junior high? Like, will this tell us who the smart kids in the junior high are? Probably not, right? It's going to be an unfair exam. Everyone's going to get absolutely bad scores, and then somebody might outperform another because they just got lucky on the random guessing and things like that. So, so in our case, this is not really what we're doing, but we're kind of doing this. Is we're trying to think of like how can we score these top tier athletes based on their things. Okay, and so it makes sense to include only people from the population that we're interested in. And so if there's a competitor who's an outlier in the much lower regard, it kind of makes sense to remove the person. But you're right, it's a valid point, and this person did make it to the Olympics, and for whatever reason, but if we try to include this person in the analysis, it can throw things off. So, okay, so we remove this, and then we can plot it, and then we see. I think it looks a little bit better. Okay. All right, and okay, so to do principal components analysis with the built-in function in R, you just use prcomp. Okay, we can do it ourselves. We can do center our matrix and find the covariance matrix, and then the eigenvalues of the covariance. Right. Principal component analysis here in R does pretty much all of this stuff, and it's in a kind of a production ready thing. Okay, so we just say do principal components analysis, and then all we do is we just give it the matrix, and in our case we're going to give it the matrix without the score column, and we will run scale is equal to true. Okay, and what scale does is it it rescales our data so that everything has a variance of 1. Okay, and so that what that does is it if we did not scale it, then if there's a variable where there's a high amount of variance, right? Like, let's say they also had to run a marathon in here, right? Okay, and in the marathon, maybe the difference between first place and last place is like 20 minutes or something like that. Okay, and then so you have these very large values, and you're trying to accommodate that. If you don't turn on the scale there, if you don't have everything have the same amount of variance, then the performance on that one event, the marathon, where there's the greatest amount of variance, will overshadow everything, right? Because in principal components analysis, we're trying to find the projection that maximizes the variance. And so if one of these dimensions has a huge amount of variance, to maximize the amount of variance captured will be pretty much to put a lot of importance on that one dimension. Okay, and so scaling it turns all the variances of all the dimensions to the same to have the same variance. Okay, and for whatever reason in R, the default behavior is that scale is false. Okay, so maybe I'll just write it up. Scale equals true makes all the variables have a variance of 1.
Do we ever want to have variance the scale false?
Yeah, I mean, if I guess it depends on the context of the thing, right? If you want to maximize the variance captured, and in this case, you know, you say, well, it makes sense that the marathon's going to be weighted the heaviest because they, you know, that event takes 3 hours to complete or 2 hours to, you know, however long it takes to complete. It makes sense we should weight that one the most heavy or something, you know, or in other situations. I don't know. It always, the answer is it always depends on the context, and probably here it makes sense to have each of your heptathlon events weighted approximately equal, so you kind of want to have fairly equal variance there. But in other cases, like I don't know, you're talking sales numbers or something, and you want to say, yeah, the $1 million contract should weigh a lot more heavy than all of these, you know, performance on these other little things that don't matter as much. Then maybe that's what you have. Okay, have a variance of 1. So when we try to maximize the variance captured, you know, one event with high variance will not, quote, overshadow everything else. Okay. All right. So anyway, to do that, you just do heptathlon underscore PCA. You know, you just create a place to store all of it, and you just do principal components of the vector that you're doing, right, and the matrix that we have. All right, and then so you just say, okay, well, what are my results here? And then this is it. And you're like, well, this doesn't, you know, what is it? What exactly is this telling me? Okay, and it just kind of gives you, it says these are the standard deviations, okay? So it tells you kind of the amount of information captured in each of these things, and then it tells you this is the rotation, and it doesn't make a whole lot of sense at this point in time, and that's okay. Okay, we can ask for a summary of our information. Okay, and then so what we see is that the first principal component captures about 62% of the variance. Okay, this is what we have, and the second principal component captures about 13%, and second and third 13 and 12%. And so if we look at the cumulative proportion of variance captured, we go from about 62% to about 75%. And eventually, if we take into account all 7 principal components, then we would have captured the total amount of variance in our thing. Okay. So what I'm going to do is I'm going to just take the first column of this rotation matrix, which tells us kind of it says the matrix of variable loadings. Okay, so this is the eigenvectors. Okay, so this rotation matrix is pretty much, if I did, it's going to be a little bit different because I haven't centered my data, but I don't know, maybe I'll do eigen heptathlon minus score, and then I just say eigen of this. So if I look at my vectors, negative 0.449, is that the same? No, it's different. I think I've got to center my data first. Okay, well. So anyway, I'll take the first the first rotation piece there, okay, and we can see what we have, and so when we look at this, is that we see that the hurdles and the long jump receive the highest weights in our thing, okay. I mean, so these are rated 0.45. Long jump 0.45. Javelin seems to be weighted a little bit less importantly, okay? for computing the first principal component analysis. Okay, and so we can take the center and the scale of our principal components. So we'll do heptathlon Okay, so this is kind of the center and the scaling variables that are used for our matrix here. Okay, and so we'll pull that out, the center and the scale, and we can apply the scale function to the data and multiply with the loadings to compute the principal component score for each thing. Okay, so here we're just basically going to project our data onto the rotation here. Okay, so I'm gonna just take our create the submatrix. Okay, so HM just is our matrix without the score. Okay, and then I'm gonna just take I'm gonna scale this using the center and the scale. Right, so pretty much this is so when we did the principal components analysis for the image, we did this manually, right? We subtracted the column means to kind of center it. Over here, I'm just using the scale function to do it for me, okay? So I'm going to tell it the center, and then the scale also changes the variance here. So, so I do this, and this creates a centered matrix here. That's what this scale function will do. And then so all I'm going to do is I'm going to take my scaled data and multiply it against my rotation. And then drop, kind of gets rid of the extra stuff here. Okay, so here this is the projection of the data onto, we project our raw heptathlon data onto the projection. Okay, and this scale function centers our data and makes variance equal to 1. Okay, and then we project by multiplying the centered data by the rotation. Okay, and then so if we look at this, okay, this is you know, we get these scores, and so this kind of arranges these in the order that we expected to see when we looked at the looking at the score. We see there's good alignment between the ordering of our heptathlon scores versus what we get. Okay, with Joyner Kersey at the top, and Jung-Mi at the end here, and we see that there is good alignment. Okay, we can take a look at using the So this is one way to do it. Another way is we could have also used predict, using the this is another way to kind of get our projected data, is to use the predict function on the principal components analysis. Okay, and then we just say, well, I just want the first column. Okay. And we get something very similar to what we have up here. Okay, so we have this, and then we have this. So it's pretty much there. Okay, if you we can plot this, and this shows us kind of the a plot of which it doesn't have the labels here, but the plot here tells us how much variance is captured in the first one versus the second and third, and remaining components. And so we can see we capture quite a bit of variance just in the first principal component. Okay, which is I think, ideal here. All right. So this plot shows the amount of variance captured in each principal component. Okay. I can create a correlation. This is the correlation between each variable. I'm sorry, between our first principal component, PCA principal component, and the actual score. Okay, and so if I can extract the score that the Olympic Committee uses, okay, and then we can look at the projection, okay, onto that score, and we can say, you know, what is the correlation between these two? Okay, and we get a correlation of around 0.99, meaning it is very strongly correlated, and we can plot these. Okay, and so we can see between this is kind of the score that here are the scores that the Olympic Committee put on along the horizontal axis, and then according to our principal components analysis, you know, this is kind of what the score that we should get. And so we see a very close alignment. There is a little bit of a fluctuation here, indicating that this person, according to our PCA analysis, they would score a little bit lower than what the Olympic Committee gave them, but that's kind of what we have, and we can look at the loadings. If we look at heptathlon, PCA, and our rotation, just looking at our first column, this would be, you know, we can scale this up by some arbitrary number, but basically we would take the long jump score, right, and then you would kind of multiply it by some constant, and then add this to their total score. So because all we're doing we're just taking, this is kind of the recipe for the 7 different events and how to put them onto a same scale to give them a score. So we would say, you know, so our recipe for coming up with a way to score people on the heptathlon would be to, you know, first center and scale all of our data so that everything has a variance of 1 and a mean of 0, and then take each of those values and then multiply that number by this constant, and then add them together. Okay, and then this comes up with some kind of scoring system that maximizes the variance captured. Okay, and you know, whatever the Olympic Committee did to come up with their scoring system does something quite similar. Okay, and I doubt maybe that they used exactly principal components analysis, but who knows, maybe they did. Okay, a biplot is another kind of tool that we might see in principal components analysis. Okay, and so what exactly is a biplot? All right, so what it says is, this is kind of how much we are weighting each of these things. So looking at just the first principal component, I don't know if you can see, it says, you know, the hurdles scores quite high over here. Okay, hurdles and long jump and shot put and the 200-meter run, these ones are kind of weighted the heaviest. Javelin, at least on the first principal component, is weighted a little bit less. Okay, the magnitude of this arrow is kind of the smallest as far as the first principal component goes. Okay, if we were going to include the second principal component to further have some to distinguish each of these individuals, then we would see that you know, the 800-meter run and the high jump are weighted a lot more. Okay, and so, you know, is there a meaning behind this? You know, what is it that holds these together versus these ones? And and it's hard to say. Okay, the biplot also plots these individuals onto the thing here, and we can see that Kersey from the USA, Jackie Joyner Kersey, scores the most extreme as far as the first principle component goes. Okay, and then we have a whole bunch of people kind of in the middle that it's hard to distinguish fully here. Okay, and so if we were looking only at the first principle component, all of these would probably end up getting something with very similar scores. Okay, and we can look at the heptathlon data, and it does appear that way. Okay, we have a bunch of people, 5972, 5975, 6087, 6101. These people have very similar scores. Okay, 6171, 6101. There's not a whole lot distinguishing 1, 2, 3, these 4 people. Okay, and these people, they all end up having very similar scores. And if we kind of compare their, which of these is weighted more or less, it's hard to know exactly what's going on. But this is a biplot, and it kind of shows you how each of these 7 variables get weighted as far as the principal components themselves go. Okay, and then it plots the data itself. Obviously, with all of the text, it can get hard to fully understand here. But here I thought this was kind of just a neat application of the idea behind principal components, where you have higher dimensional data, seven dimensions, 7 bits of data here, and we're trying to boil it down in a ranking system that's kind of fair in that we can distinguish your gold versus silver versus bronze athletes here down to a single dimension. Okay, and then so we would plot all of this down to just one. Okay, I guess we're gonna run out of a little bit of time. I mean, not run out. Finish early today as far as this goes. How's your homework going as far as? Yes, question.
I have a question.
Okay.
You said that if we have a tie,
right,
we should base our tiebreaker off the nearest neighbor. Do you want us to use what the nearest neighbor then says is the class?
So it should be nearest neighbor among the tied classes, if that makes sense.
Okay.
So if it's like 3A, 3B, and 1C, and the nearest neighbor is C, C should not be the classification. Okay, it should be between the 3A and the 3B, which one has the nearer neighbor. Okay, so is it A that's closer or B that's closer as far as the one nearest neighbor. The logic there gets a little bit complex, but it shouldn't be too terrible. Okay. Everything else? You guys have all started, right? So, okay. I think it's non-trivial, the coding up of the assignment, but
It's non-trivial.
it's non-trivial, but it's also, it should be manageably doable as well. Okay, and this, of course, in real life you would just use the pre-production, the formulas or the functions that have already been implemented. There's a naive Bayes function. There is a k-nearest neighbors function implemented already in R, but the assignment is to force you to think about these algorithms yourself. Okay. All right. Well, I do have office hours today. If you guys have questions, and we'll end here, and then on Wednesday we'll take a look at some of the clustering stuff. Okay.